So this is the basic idea of bits. So how the quantum bits are different from the classical bits. To get this idea, let's assume that we could write the single bit into a more convenient way to describe the quantum bits. So consider 0 as a 0 ket vector, and we could write it as a column vector. And similarly, we can write the bit value 1 as a column vector 0, 1. So classically, bit can have only, or a state can have only one bit value, or like it can have only 0 or it can have only 1. But a qubit is described as the superposition of the two bits values, and it can be described as the state having two uh, two bit values at the same time. And this phenomena is usually called the superposition of the two bits or two states, where alpha and beta are the amplitudes of the state vector, and they are usually associated with the probability. And if the alpha and beta are not, or the state vector is normalized, alpha and beta usually follow this normalization condition. So it can be seen as in the diagram as we have a state vector psi, and alpha and beta are associated with the axis describing the bits or state of 0 and 1. So beta described that how much state 1 we have in state vector psi, and alpha describes that how much state 0 we have in state vector psi. So if we have alpha is equal to 0 and beta is equal to 1, we have the state 1 deterministically. And similarly, we could describe that if we have beta is equal to 0 and alpha is equal to 1, we could predict that the state vector is in 0 state. But if they have half of uh, uh, probability or half of amplitude, we cannot uh, predict the outcome of the state vector after the measurement. So this is the concept of the qubit. So physical interpretation could be seen as the two-level system. So we have a two-level atom which have two orbits, we could say, and we have an electron. So classically, electron can be in a zero state or in one state. But quantum mechanically, it can be in the superposition of 0 and 1 state, or we could say that if we want to describe the two-level atoms as a qubit, the electron can be in state of 0 and 1 at the same time. And this is the weird thing associated with the qubits, and make the uh, quantum quantum mechanics quite weird and non-logical, and quite non-intuitive. So similarly, we have the idea of qubit. In qubit, we have a two-dimensional vector space, and a vector can be spanned by uh, only two bases or two basis vectors. But in the idea of or the concept of qubit, we have d-dimensional space, and the state vector can be spanned by the d vectors, and associated amplitudes are also in the number of d, and we have d amplitudes associated with the d ket vectors that span the whole space, and in terms of which we can describe any vector. And the normalized qubit follows that condition of normalization as previously we seen in the case of the qubit. So similarly, we have orthonormal basis for qubits. The most standard and most used bases are the computational basis, and they are 0 and 1. And these bases are associated with two-dimensional space. Similarly, we had the Hadamard bases, and they are just the off-diagonal bases from plus and minus, and we could see them as the making a 45 angle with 0 and 1. But they are orthonormal to each other, and this could be verified by taking the inner product of plus and minus, and we will see that we will end up with the answer of 0. So in vectors, in two-dimensional vector space, or in the case of quantum bits or qubits, we can use these two basis sets to describe any vector space. And this depends upon the our goal and the condition we want to achieve in our experiments. So today we explored what makes QKD unique and laid the groundwork with key mathematical tools like complex numbers, bra-ket notation, and qubits that will be indispensable throughout this series. So if you found this helpful, don't forget to like, share, and subscribe to Quantum Curious for more lectures on QKD and quantum science.